So hi, hello everyone again, Microbehunter here and welcome to another Saturday live stream, Saturday microscopy live stream. So I have just hearing in my echo here. Okay, I think now I'm fine again. Okay, well, welcome again, as I just mentioned. Today, as you can see, I've prepared a couple of microscope slides with different types of crystals on here. Look what I got here. I'm going to shift over the camera a little bit. Isn't this great? Yes, I was sent 10 different chemicals for microscopy by a microscopy friend, and I would like to say, of course, again, thank you very much for having sent these substances to me. Look, yeah, it's this one over here, for example, is sulfur. Yeah. Urea, there are a variety of different substances, and what I tried to do is I tried to crystallize them. So I made those slides here a few hours ago, and I would like to simply show them to you and give you a little bit of advice if you also would like to try a little bit of crystallization. It's not the first time that I'm talking, that I show you how to make crystals to be looked under the microscope with polarized light. I've made several videos already, but I've never used so many different substances as today, right? And so this is going to be a little bit, was also a new thing for me. And then I also got myself something interesting here that I would like to show you. Look at this here. This is clear nail gel. Okay, it's not a nail polish, it's very similar to nail polish, but it cures in ultraviolet light. And I found out there are possible method of actually using this to make permanent slides to protect those crystals with a cover glass. And for curing this, I'm going to use an ultraviolet flashlight, which I've got over here, right? So I'm going to try to do that. Again, it's a little bit, everything is a little bit experimental as always. I mean, that is part of the fun part of these live streams. Yeah, and so kind of hoping that this inspires us all a little bit, okay? So that's a little bit what I intended to do. If we have a little bit of time left, I do have, I did receive 2 more antique microscope slides, which I ordered, which I can also show you. I know it's a little bit off topic then, but it doesn't matter. For those of you who are new to this live stream, please feel free to ask questions in the chat. Maybe also short info if the sound is okay, because some time ago I started to talk and there was no sound. If for whatever reason the live stream becomes interrupted, I will try to restart it again. So, but it might be on a different link, because once some time ago I had actually some issues here as well. Okay, I see that there's a hello from all around the world. Okay, everything seems to be fine here. As always, a very international audience that we have today. Yeah, and that's always very great. So what I'm going to do now is the following: a little bit of a little bit of background information. If you want to make crystals for microscopy, essentially all you do is you take a little bit of solvent. In many cases water is enough. In some cases alcohol is also fine, and you mix a little bit of whatever substance you want to use with a little bit of the water with the solvent, and you spread it. It starts to dissolve, and you allow the water to evaporate, and then with a little bit of luck and a little bit of patience, you'll have crystals forming. This is not always easy, okay? And I would like to simply talk a little bit of some of the problems that there might be. So for example, look at this one over here. This one that I made in the morning today, so over 12 hours ago. And you see that there's still a drop here which is wet, okay? And so it did not completely dry, and the reason is because some substances like to attract water so much from the air that it doesn't dry properly. You know, so I've the same substance over here, number 1, that is potassium carbonate. Okay, you can see it also remained, I increased the concentration here, and it kind of remained still very moist. I heated it, and this actually started to result in some crystals forming, because by heating it up you evaporate the water. But I'm going to show this to you now again, because I just after a couple of minutes, it was quite surprising, because you still do see crystals, of course, but let me see, where are they? I need to refocus again. Here we go. Yeah, here are some of these crystals, but there was somewhere on the other side here. Yeah. Essentially, And let me find it here. For example, here that's a nice place. Yep. If you look very carefully, let's go up a little bit with the magnification here. You're going to actually see that those crystals here are round. Just a couple of minutes ago, yeah, they were still kind of had edges and had corners, sharp corners, because it started to crystallize. But then I think the moisture from the air got attracted to the extent that the crystal started to melt again and started to round off. Yeah, so it was kind of reverse crystallization. So basically, it's the moisture of the air that started to dissolve the crystals again, right? Something that's quite a fascinating thing, and this actually now motivates me to maybe I have to get some kind of a hot plate or something to speed up the crystallization process. Okay, so basically, these are some of the just one of the things, some of the challenges that you might experience here, and. Yeah, I would like to simply show you now some of the crystals, and I would like to also dissolve some of them again, because actually crystallizing them out will actually take a few hours, right? And of course, we don't have that time, but what I'm going to do is I'm going to try reverse crystallization. So basically, I'm going to add a little bit of solvent, and then you can see how some of those crystals start to dissolve again. What I'm going to do first, however, is I'm going to run you through some of the substances that I actually have got, okay? And let me remove this slide here and numbered, so you can see a numbered slides here. And yeah, these are the substances: potassium carbonate, ascorbic acid, copper sulfate, citric acid, tartaric acid, alum, which is aluminum sulfate, urea, salicylic acid, which is the substance in aspirin, potassium ferricyanide. Don't let the cyanide word scare you off. It doesn't. It's not poisonous. Okay. And sulfur, as a matter of fact, the substances here. I mean, you shouldn't eat them, but they're not highly toxic. Yeah? Well, maybe the copper sulfate. Microorganisms don't like copper sulfate. Okay, that's why you shouldn't dump those into the water. And here they are, these substances. That's, for example, urea. Okay, aluminum sulfate, and so on. Yeah, this one, very nice red one. Yeah. So thank you again. For having sent me those substances here. This, however, is not going to be the first or the last time. It's the first time that I'm going to put them under the microscope today, but it's not the last time, because in next upcoming days I would like to optimize this process a little bit, and I would like to make some nicer crystals here. So as always, before I start to show you some of these things here, I would like to give you a little important demonstration, and the importance of this will become clear very, very soon. And that is there is one problem if you put a water droplet on the slide, and this problem is that the problem of surface tension. It's very difficult to spread the liquid over the slide, because as the water evaporates, it starts to pull together again because of surface tension, and then you have a very small area with a very high concentrated crystal solution. You don't want that. You want the liquid to spread properly and evenly. And in order to do that, what I've done here is I've of course taken some water and I've added a very small amount of liquid soap. And this soap, only very small, so that it does not interfere with the crystallization process. And this small amount of soap actually breaks the surface tension and makes sure that the water is able to spread more evenly over the slide. Okay, so this is something that I would like to show you now, the effect of surface tension. It's just a simple demonstration now that some of you might already know. Okay, here I've got some liquid soap, okay, just for washing your hands. Over here you have a Petri dish, and I'm going to add simply a little bit of water, okay, here. And I just want to show you what happens. This is regular water, and I've got some pepper here, okay. So this here is pepper, and I'm just going to do the following. Have some of the pepper floating on the surface of the water here. Okay, so so the pepper does not sink, it likes to float on the surface. And now look what happens. I'm going to take now a little bit of this liquid soap. I'm going to dip this plastic spatula into the liquid soap, so there's a very small drop here. You almost don't see it. Okay, and look what happens if I carefully touch now the water. 3, 2, 1. Pew! Do you see how it spreads apart? Okay. Yeah. So what happens is that the soap molecules, they will actually go on the surface of the water, will kind of and push everything on the side, breaking the surface tension. right? And that is actually something that we want. We want the water drop not to be too small, but to actually spread. Okay, and in some cases, maybe if you're lucky, then in some cases the substances that you're adding to the water when you're crystallizing something, maybe sometimes this breaks the surface tension, but not very often. Okay, so this is actually one of the things here why I added a little bit of soap to those substances here. Okay, what I'm going to do now is I'm going to give you a demonstration on one of those substances what I have done. Okay, and however we are not able to wait until it crystallizes because it will simply take too much time. That's why we're going to be looking at the others. And what I would like to do first is I would like to simply give you a little demonstration on concerning citric acid, not citric acid. Where is this? Vitamin C. It's ascorbic acid. Here it is. Okay, that is vitamin C, pure vitamin C. And what I'm going to do now is I'm going to take a pipette. Here it is. And I'm going to simply add a small amount of this water with a little bit of soap. On here. You probably have already seen me do this before already, and you can see that because of the soap in here, the drop kind of spreads more easily. Okay, so that's actually good. And then what I will do now is I will now add a small amount or a larger amount of this citric acid. Okay, let me quickly rinse this here. I've got some water here for rinsing it, because I always want to make sure that this is clean. I take a little bit of this here and I put it into the droplet of water. It will dissolve a little bit. Some of the crystals will not completely dissolve. That is fine, because this will act in as so-called crystallization seeds. So crystallization will continue there. I'm going to just put this now under the microscope so that you see how this looks like. Okay, so this here is vitamin C. A very nice thing to observe. And this is how it looks like. Okay. And we have already got a saturated solution. That's why those crystals, the remaining crystals, do not continue to dissolve. And then what's going to happen is that as the water evaporates, more and more of the crystal is going to start to recrystallize. Okay, maybe I'm just going to go down a little bit with the magnification so that you see a little bit how this looks like. Okay, and you can also see that many of these crystals are not quite as sharp anymore, and for this reason, it is kind of a sign that it started to dissolve a little bit. Okay, so this is basically, this is basically the substance here. And now, how does vitamin C look like when you actually allow the water to completely evaporate? Okay, so this is something that I also would like to show you now, but I'm going to put this a little bit to the side here first, and I'm going to label this. So citric acid, no, it's not citric acid, ascorbic acid, that's vitamin C, is number 2. I'll just put a label number 2 on here so that I do not confuse this. And then the one that I made in the morning looks like this. And okay, let me put this back in again, turn up the light intensity again here. And you see that basically these are very flat crystals that have formed. And depending a little bit on the amount of citric acid and the speed of crystallization, you do get different patterns. So over here, I've tried it a second time as well here. Okay, you see that there's still some non-dissolved crystals. And you can also see that new crystals started to form on the slide itself. So it's kind of interesting a little bit. I was kind of wondering, you see this quite often as well. Let me turn on the, how is it possible that even though here we have got this vitamin C crystal, you've got some crystallization happening over here directly on the slide, but why is there this area around it without any crystals so much. Yeah? And I think the reason is that all of those, the vitamin C that was here, started to be deposited on this main crystal here. Yeah, so it kind of diffused and then it started to become deposited here, and that's why we have an area here of very little vitamin C. Yeah? So there's a question, what does it look like without polarization? Yes, as a matter of fact, I wanted to show you as well. This is how it looks like without polarization. So this is a regular bright field. Okay, you still see the patterns, but not so many colors. Yeah? So what I'm going to show you now as well is the following. I do have, because I've got built-in polarization and all these things, but what you can do as well is the following. You can use you can use polarization filters. Look what happens when you turn them. You can see actually that it becomes darker, yeah, and then brighter again. Okay, I don't know if you're able to see this, but depending on how you turn this what you can do is you can place one of these filters over the lamp, which you cannot see right now, and the other one, I'm going to use the low power now, and the other one you can place basically, look at the top, okay, between the objective and the specimen. You might have to refocus, okay, and then I'm now rotating the lower one, and you can actually make it darker. Some of these, you can actually see that there is some, you can observe the different colors. Looks quite nice, like quite pretty. By using this cross polarization, it looks again different than with my built-in polarizer, because there's some other optical elements in there as well. Yeah. Because I've got this technique called DIC, which also uses polarized light, but is different than just using crossed polarized filters. Okay, so when you turn it again, you see that the background starts to light up, or you can also turn the one over the lamp like I'm doing right now. Okay, so there are plenty of things to experiment around with, let me go back here again to the desk view, and here we are again. Okay. I do have occasionally also some questions which are off topic, which basically is fine. And there is a question here, you mentioned in a previous video that viruses are too small to see under a microscope. Well, under a light microscope. You can see viruses in electron microscopes. Okay, so how do researchers study viruses? Well, you analyze their DNA or their RNA, their genetic material. Okay, so what I would like to do now is before we look at the other things here, I would like to show you something that I would like to illustrate this to you. So number 6 is alum. Okay, you know what? I'm just going to try it with this slide over here. I would like to, let me see if I have some larger cover glasses. Let me check. I don't think that I have them here. No, actually I do. That's good. Okay. So what I would like to do is I've got here a substance called aluminum sulfate, and I would like to, because the crystals here are very delicate, I would like to kind of make this protect them a little bit. Okay. The question is now, how do you do that? Well, it's very clear that I cannot put mounting medium. Normally what you would do is you would put mounting medium on the slide, and then you would basically put a cover glass on top. This is not going to work, because many mounting media are going to dissolve the crystals, or the refractive index between the crystals and the mounting medium is not right, and then you don't see them properly, right? So what you need is, actually I would like to put a cover glass on top here, but I would like to make sure that it's still surrounded by air. So I want to make a dry mounted microscope slide, and I'm just going to use those gigantic cover glasses now. Look, I don't know, they're pretty big, okay? And there is now the following problem, and I do have a suggested solution for this. If I now take this cover glass, put it on top here, of course I can use sticky tape to glue it down on the edges. But if I use some kind of a liquid glue, or if I were to use some, I don't know, clear nail polish, which is very thin, what's going to happen is that it's immediately going to be flow beneath the cover glass, and it's going to touch the crystals here. right? So I was kind of wondering, I mean, is there not some kind of a possibility to actually connect the cover glass without making the glue or the mounting medium or whatever touch the crystals, right? And I found actually something, and I'm not saying that this is the best solution. I'm not saying that I recommend it or that I'm not recommending. We're just going to experiment with this, okay? And then you can try it yourself, and then you can let me put the pepper away again. And then you can, decide yourself whether this is something meaningful or not. I just want to demonstrate this. And this is to use this ultraviolet curing clear nail gel, which was surprisingly expensive. I think I paid around 15 euros for this bottle here. Kind of hoping to, use this as a mounting medium. But it's too thick. It's very thick. It's really like a gel. So what I'm going to do now, and again, this is something with the crystals. It's the first time that I'm trying this. Okay, look, it looks like this. It's really like a gel, thick, way too thick for a as a mounting medium. But you know what? I'm just going to put it a little bit here. Then I'm going to put some here. Okay. See, it's very thick, like honey. And then I'm going to glue the cover glass here on top. Okay, and because it's so thick, and so viscous, this nail gel, therefore, even if the crystals are a little bit larger, it's going to work. Let me close this again. And then what you need is an ultraviolet flashlight. This is a bluish light. And look what you have to do for 1 minute. You have to, and you are not able to see. I don't know. Are you able to see this? Yeah, it's actually bluish in color. And for 1 minute, you have to shine the blue UV light on this nail gel. Let me put this away just for safety reasons. I don't want it. Yeah, and it says here, I think 30 seconds to a minute. And this will actually cure the whole thing, and it will be turned solid, relatively solid. Okay, and basically, this is I would say, a technique that I'm going to try to explore a little bit more, whether this is actually something feasible, because it actually cures quickly, just in a minute or so, and maybe there are even those, look, there are even those devices where you can put your fingers in here for if you're putting this nail polish on your hands, and so maybe last time. So I don't know if this is enough or not. Yeah, and it's already solid. Okay. Yeah, it sticks. Okay. So this is actually a possibility. Maybe if the cover glass were a little bit smaller, one could apply also something on the edge here, right? To completely seal it off, but now at least this is better protected. I'm not saying that this slide is going to last an eternity, but at least that's simply one thing that I'm experimenting around with. But because I'm already holding it in my hands, let's have a look under the microscope how it looks like. And this arrow, let's put the arrow away. Okay, so this is aluminum sulfate, and again, let me. This is not, and let's do it like this, let's do it like this, and like this, and like this, and not all of the, so here we go. Let me put this back in again to give it a little bit of color, because color is nice. And these are the non-dissolved crystals, and I think just before we could also see. Yeah, I lost it again. There were some of them that started to reform. Nope, that's a little bit of dirt. Maybe this is a little bit from the magnification, a little bit too. Here we go. Here it is. Very faint one. Okay. If you see something like this forming, then these are actually crystals that started to form out of the solution. And those are still those crystals from the original substance, which have not completely dissolved yet, and sometimes there was also recrystallization happening there. Okay, yeah, but that is basically one of those crystals that formed by recrystallization. So I'm going to have another look here. So let me see. Let me see again here. Wondering why they have not invented cover glasses with built-in round walls for this purpose. Surely you can 3D. Yes, I think what you what you mean is with those round walls, some kind of spacers. As a matter of fact, yes, I already 3D printed some spacers, and there are some. There are also microscope slides available that are concave. Yeah. So indeed, these they are well slides, or you can have spacers. So, Sir Microbehunter, so is this then the regular nail gel or UV gel, or does UV light also work with regular gel? No, UV light does not work with regular nail polish. This is specifically UV. Yeah, I have to change this again. Square this here. This is specific. It says here it's LED UV curable. Okay. So I don't know. I think what they do is they put this on. You put some paint. How do you call this? Some nail polish on your fingernail, and then I think this is put over it to make it shiny. I don't know. I'm not so much into cosmetics, so I don't really know much about this. The only thing is that I was specifically searching for one where you can use ultraviolet light. Yeah. So. Is it safe for your eyes to look directly at UV light? Generally, it's never a good idea to look directly at ultraviolet light, but it depends a lot on the duration, of course. Yeah. And ultraviolet light also has a spectrum, so some wavelengths are not quite as problematic as others. Under what name can you find such UV device stores a UV torch? What they have is, you know what? Just a second. Here, actually, I have a box here. It looks like this, the UV gel lamp, and I just unpacked this here as well to show you. Yeah, it looks like this, and there is some UV, and then basically people put their fingers in here to get it cured. Honestly, I don't have a good feeling putting ultraviolet light on the skin, but apparently this is tested and apparently it's safe, I was told. Obviously, otherwise it wouldn't be allowed, right? So this actually shows that not all ultraviolet light is the same, right? Of course, I wouldn't look into the whole thing too much, but this is actually specifically designed to be used for fingernails. Okay, so this can also, and I have also used this already before. I put my microscope slides in here. Okay, so just wanted to show this to you that this is indeed a thing that is possible. Again, I'm not saying it's a good solution or a bad solution or so. I just want to present it to you as a possible option. But I would say let's go back a little bit. Let's go back a little bit to the crystals and have another look at those. So why do crystals form in the first place? Well, crystals form because the substances they have a certain shape, and when the liquid evaporates, when the water evaporates, then they cannot be held in solution anymore, and they start to stick together, in a very organized way. Yeah. So therefore they will then start to form solids. Okay. So. Yes, so I'm going to quickly go through here. This here is, number one, is potassium carbonate. Let me quickly take this out again. Okay, number one, and that is the one that we looked before, and which basically this light really doesn't like to dry. Okay, this is really interesting. Yeah, and as a matter of fact, it starts to become more and more liquid the longer I wait, and it seems to really absorb a lot of the moisture from the air. And now even those crystals that were present before are gone. Yeah. So because yeah, it's so it's attracting the moisture so much, and those crystals that are left over here, yeah, they look round because they're actually in the process of also of dissolving. So that is the first one. So that is this is potassium carbonate. Where is the you probably want to see the original as well. I have to. Here it is. Okay. So I just want to show it to you as well here. This is just how the powder looks like. It's just some white powder. Okay. And it dissolves extremely well in water. I was actually quite surprised. Yeah? And therefore you always have to keep it close to prevent moisture from actually reaching the substance. Okay. So I think very difficult to crystallize, but it does work if you heat it up. Okay. Let me put this away. So number 1. So this one over here, number 2, is vitamin C. We just had a look at this. Okay. We just also made a slide of this here, and let's see how this slide is doing right now. Okay. So this is again the ascorbic acid, the vitamin C. Yep. Look, it's starting to, the crystals start to, some of them start to show some corners now. This basically means that crystallization is starting to take place. And depending very much on the temperature, on the concentration, and so on, essentially the shapes can look very different. So yeah, see, these start to recrystallize quite nicely, and what you can do is with a lot of patience do a little bit of a time-lapse video and then see how they're actually growing. Yeah. Okay. Can you compare the growing of the crystals you are showing us tonight with the growing of rock crystals? You mean actually the crystals that you can find in minerals in rock? Well, sometimes those crystals found in rock, for example, when you're collecting some minerals, I think there are a variety of different ways how they can form. And some of them can actually form when very hot, the hot molten rock is actually starting to cool. Then certain minerals start to crystallize out because as substances, as the solvent and substances cool, they're not able to hold the substances as well anymore. So for example, warm water is able to hold more of the substance than cold water, and as it cools out, it starts to crystallize out. Okay. Why are there so many air bubbles in the potassium carbonate? I think that's a good one. I can actually show it to you briefly as well. I think it could be that maybe the potassium carbonate starts to break down, also forming carbon dioxide. Okay, so this is quite an interesting thing, and maybe if we just continue to watch this a little bit here, we can actually see that the crystals actually do start to slowly grow. Okay, because just a few minutes ago they were much smaller, right? So this is actually something that I've also done in the past. Do some time-lapse videos, yeah, and usually when the substance is depleted, then the crystallization process, of course, stops. Okay. Let me turn the arrow off again. Okay, really nice things. But again, what I'm demonstrating here is pretty, as I say, off the cuff, a little bit improvised. And if you try to optimize the conditions, and you can get really beautiful results. Okay, so you know what? I'm going to, because there was a question here. I'm just going to put some of this potassium carbonate also under the microscope now, just so that you can see how this looks like. And I'm going to do it like this. I'm going to, because of the bubbles, you know, so then you can actually see the dissolving process. So that's the potassium carbonate. Where is my spatula? I misplaced it again. Oh, I have, here it is. I had it in the water. So let me dry this again a little bit. So you would like to probably see what I'm doing. Let's move this up a little bit, or let's move this over here. So I'm going to put, look at the static electricity here. So let's put this back in here again. So you close it off. And I put this directly under the microscope, and then I'm going to add some water. Okay, but because there's the danger of the whole thing falling off, I will now add first a cover glass to kind of protect it a little bit better. And then I can always add a little bit of liquid. So I just put a cover glass on top, and that's how it look. And you're able to see those things here, okay? And this is basically how the powder looks like. And then let's add a little bit of some of the liquid here. Yeah. Now in this case it's not so important whether it contains the soap or not, because there's a cover glass on top anyway. So, okay, and I'm going to now add a little bit of the liquid. You can check on top. Okay. Okay, here it touched it. Oh, okay. It's going. Well, I need to add a little more maybe, because as it's starting to. So now we can actually see it dissolve. And it looks like there are bubbles coming off, right? So maybe it is indeed air that is trapped, or maybe, here are lots of bubbles, right? So, or maybe indeed carbon dioxide, I don't know, right? Because it's carbonate, so maybe it forms hydrogen carbonate, and then you also have carbon dioxide forming. Yeah. And even those bubbles look kind of nice. Yeah. And then what you have to do is you have to wait somehow until this dries again, and then you basically are able to see hopefully some recrystallization happening. Almost all of it is already gone. Here it is. Here's some more. Yeah, you see actually how it becomes smaller and smaller. Go down a little bit with the magnification here so that you see. Yeah, because of capillary action, of course, the water is also moving. And as the crystals become smaller, of course, the film of water between the cover glass and the microscope slide, of course, also, yeah, lots of bubbles. Yeah. See, and pretty much almost everything's already gone. This is there's so much. There's so many bubbles. I almost think that this is not just trapped gas, but it probably is to a certain extent also carbon dioxide. Yeah. So that's kind of how the dissolving process looks like. Okay. Yeah. Simply because you wanted to know about the about some of the bubbles. Okay. So let's put this away again. Let's start to have a look at some of the others, because what time is it? It's already 38 minutes. So number 2 is ascorbic acid, vitamin C. There is another vitamin C slide that I've got here, because vitamin C is actually quite a nice specimen to look at. Okay, so again here. So that's one that I also made already before. You can see the very typical flat crystals that we see here. Yeah. Like a little bit like modern art. Yeah. So, yeah, that's very typical for difficult. Vitamin C was actually quite difficult to do if you do not add the dishwashing, not the dishwashing, is the soap, because it will actually start to form very thick crystals otherwise, because the water droplet will pull together and it will be too thick. But because of the soap, you have actually thin layers forming, which is quite nice. So I'm quickly going to have a look again at the comments here. Okay, hoping that I don't overlook anything. I always use a cheap USB coffee cup warmer to speed up the drying and crystallization process. A USB coffee cup warmer? Wow, that's an interesting. Okay, thank you for this. I never thought about that. Okay, I was already thinking about getting some kind of a metal block that I could actually warm up or cool down. So that's interesting. Would dishwasher soap also work? Yeah, any form of detergent would probably work. Yeah, I just used regular soap, liquid soap, but dishwashing soap, we only need a very small amount. Okay, I think I'm going to have a look at this into the USB, yeah, coffee cup warmer. Didn't know that these things actually exist. So let's move on. Yeah, let's move on a little bit. The desk here. Yeah, look. There's still so many substances that I have. And what's another one here? So let's put this away. The number 3 is copper sulfate. Ah, yeah, that's an interesting one. This one has also given me a little bit of a headache. The copper sulfate. And the copper sulfate looks like this. Okay, nice blue color. Okay, and yeah, it's used for a variety of technical reasons. But what I read is you should not put it, you should not dump it down the drain because water microorganisms really don't like the copper. We, yeah, of course, already know, or some of you might know that copper and other metals are indeed not good for yeah, water microorganisms. Okay, that's one of the reasons. Apparently why they're copper coins, because microbes don't like to grow on copper so much. So, and I placed also some of this substance on a slide and allowed it to dry. It also took quite a long time. And then actually, as I said, well, actually, the crystals, they do not look very flat, right? Indeed, however, recrystallization did happen. Okay, recrystallization did happen because, oh, forgot again. Here we go. Because some of them, maybe that's actually not the nice one here, because some of them started to look again a little bit in one of the very small places. I could actually see this happen, but I can't find it now again. Yeah. But let me open this a bit more. Yeah, that's always the thing here. Yes, for example, here, that's one of those examples here. You can see that this crystal here has a very sharp corners. So this actually shows that it started to recrystallize. Yeah? But it did not, this crystal did not make did not like to grow very flat on the slide, but actually also grew up a little bit into the air, so to say. And therefore, yeah, it's quite different than, for example, the one that I just showed you with the vitamin C, which like to make very flat crystals. Yeah? But you can actually see simply from the sharp corners that these are newly formed crystals. I mean, I don't know, if just for the fun of it, what we could try to do is, let's go down with, I don't have this, so here we go. I'm going to put the polarization away now. Yeah. What I could try to do now, just for the fun of it, I'm going to add a little bit of water here. Let's see how this actually works, what's going to happen. So, okay. And yeah, you see the crystals, of course, melting again. And it will form then a saturated solution, and then it will start to recrystallize. Just a little bit of playing around here. So let's move on. And this is another one that I tried. So let me see, where is this here? Yeah. Again, there seem to be some trapped air bubbles in there. That's completely normal. And then if we wait a little bit, or if we put it on some kind of a heating plate, then we should actually see the crystal start growing again. Okay, so I think I've prepared another one, number 3. That's the same one here. The crystals again look a little bit different. It's the same one. And here, indeed, I was able to, I don't know why, but here the crystals indeed were much flatter. Okay, let's put it back here again, a little bit of view and polarized light. So it's some really interesting. And this here, this long structure that you see here probably was some kind of a dust fiber which acted as a crystallization seed. Yeah. You see, there's some, yeah. So let's just for the fun of it, let's try that here as well. See how basically how the substance actually starts to melt. If you want to see a really nice, I mean those here are a little bit improvised now, but if you want to see really nice crystals, and some weeks ago I made a video about soy sauce. I put some soy sauce under the microscope, allowed the soy sauce to dry up, and this really made very, very nice crystals. Just check just a few weeks ago in this channel. Yeah, yeah. It's quite interesting to see how the different conditions, like the concentration and also temperature, how they actually impact the appearance of the crystals as well. Yeah. So what is number 4? Citric acid. This was also difficult. Okay, citric acid readily available. Also, unfortunately, I got some water now spilled here, and I also want to show you a little trick here of how you can improve the chance of actually citric acid from forming crystals. It takes a long time, but the citric acid crystals also generally also make very nice patterns. Let's put this away here. So citric acid is, many of you probably already know, or some of you might already know it, because it can be used also in cooking, for example. Yeah, it's very, very sour. Citric acid now. Here, and yeah, this is a very typical thing here. And citric acid likes to make those very flat parallel structures, almost like a fan, yeah, or feathers even. And what I've done here is the following: is I made a saturated solution of citric acid on the slide, and again, just like before, it did not really dry very quickly. And so what I did is I added some additional dry citric acid crystals into the solution. And then this acted as a crystallization seed, and then this is where more crystals started to form. Okay, we can play a little bit around here with the colors. Another way of how you can make crystals, but this does take a few days, is by taking a small amount of citric acid, putting a cover glass on top, no water, and then melting it over a hot plate. It's got to be quite hot. And when it melts, then the citric acid will spread beneath the cover glass, and then you have to wait a few days until it recrystallizes. So you do not always have to put it into solution, but sometimes simply melting it by heat also works. If you heat it too much, it's going to burn the citric acid, and then it also doesn't work anymore. Yeah. So yeah, I'm quickly checking here. Could you explain how retardation plates work? Is it possible to make it a do-it-yourself project? Retardation plates are, I think, the so-called the lambda fourth plates. And what they do is they convert linear polarized light into circular polarized light. Yes, it is possible to do this as a do-it-yourself project. However, I had some problems getting those lambda fourth plates. You have to simply order them. They are available. I know that many in physics labs and schools and so on, they use those. But these are not quite as commonly available. Yeah. So what is the visible magnification for crystals, bigger ones, so that I can use Olympus 40X? Would I see anything? Well, I'm using right now the 10 times objective. Crystals, actually, you should only use very low magnification. Even 4 times is often enough. The reason is because some of the crystals are fairly thick, and you do want to have a proper distance between the objective and the microscope slide. Yeah, and going up with the magnification really doesn't add a lot. I mean, this is now more than 20 times. I don't want to go, but you don't really gain a lot because you're kind of losing a little bit the overall appearance. Yeah, I've had to put in the condenser again. Yeah. So this here is citric acid. Okay. And so I remember you said that for substances that have high surface tension, we should use alcohol. That is also something that I've tried. So for example, instead of mixing in soap, it is also possible to mix in some alcohol. As a matter of fact, this might even help dissolve some of the substances. However, be aware that the alcohol will evaporate first, and then you have we're left over with is again water, and this again has a higher surface tension, and this might result in the same problems. Yeah, so it is something that I've tried. It does work, but again, it has to be optimized. So again, mixing alcohol, water with the substance because the alcohol also breaks the surface tension. Yeah. I love these things here. I mean, they look very pretty. Yeah. So this was now what number? This was now citric acid, tartaric acid. Number 5. Where is number 5? Do I have number 5, 6? No, here it is. Okay. Look, also quite a little interesting thing here, and I made this 12 hours ago. This slide. Look, over here it crystallized. And over here, it remained wet. It's really interesting, yeah. And as a matter of fact, it could be maybe that, maybe there were no crystallization seeds present. I don't know. So what I'm going to do is I'm going to use this wet one over here, and under the microscope, I'm going to add some more of this, okay, to see if this can actually initiate crystallization or not. Yeah. So let's put the other one, the citric acid one, away. And let's put this one in here. This is number 5, yes, tartaric acid. And squares, here we go. I mean, some of the crystals do look kind of similar. Also this fan-shaped appearance. Okay. Okay, let's adjust this a little bit for better contrast. And over here, this is the place where it did not crystallize yet. Yeah, so you see, there's liquid there. Yeah, but for whatever reason, it didn't crystallize. I don't know why. Again, maybe the substance likes to attract moisture from the air very much, so that maybe here a little bit. I don't know. Okay. But what I'm going to try now is, see here again at the borders. Normally crystallization sometimes also starts at the borders. Maybe over here or something. I don't know. Yeah. So what I'm going to try now is I'm going to simply leave it here. So I'm right in the middle, and I'm going to take, I don't know, I would say maybe one of those tips that I have here. Number 5. Where is it? Citric acid. So that's it. Over here. I'm going to again here. I'm going to now take a small amount here. I don't know if it's this. No, I see. I'm not able to pick anything up like this. So I'm going to use again my spatula. Always rinse it off, dry it off. Okay, and let's take a little bit here. Look at this. Look at the how do you call it? The static electricity. And I don't know. I really don't know what to expect. I don't know if this is actually going to work or not. So let's go down with the magnification so that there's a bigger distance. Just a second, I need to swing out the condenser again. So, and let's see how this works. Okay. So here are some of these crystals. And maybe, look. This acted as crystallization seed, and now crystallization actually starting again. So those crystals are now growing. Okay, again, slightly higher. Okay. Sometimes what is also possible is that you try to scratch a little bit the surface of the liquid, and sometimes this will also start to initiate crystallization. Looks also kind of pretty now. Yep. Here we go. In a lower magnification to get a better overview. Okay. Yep. So sometimes it wants to crystallize, but it can't because there is no starting place, so to say. And then kind of, yeah, you kind of help it a little bit, and then it will take off and it will start to proceed. Yeah. Okay, I think you get the point. Yeah, so plenty of things to experiment. Yeah. Let me see a little different place. Maybe what about over here? Oh, yeah, here as well. Sometimes crystallization will start quickly and then it will stop again. Yeah, so I think it depends all quite a bit on the concentration of the substance. And because it's so fun, you know what I'm going to do? I'm going to end up destroying it again by adding it again a little bit of water. So let's see. And everything's melting down again. Because by adding water, of course, it's further away from the saturation point. And it's starting to dissolve. So several years ago, I've made quite a few nice pictures that I put up on my wall, using crystals. So, okay. Let's move on a little bit. What time is it? Oh, it's almost 1 hour already. Yeah. So this is number 5. Number 6. I quickly go through the others. Number 6 was the one that I made before. It was the alum. Number 7. What's number 7? That's a cool one. Number 7 is urea. Okay. Urea. It looks. It comes in little pellets like this. Yeah. Also dissolves very well. And was very easy to crystallize. So the urea crystals were formed quite easily, and the urea crystals look like this. Okay, and again, let's get a better overview here. Yeah, at low magnification, thin thread-like structures. It was actually interesting. At the beginning, they did not form, and then all of a sudden they formed very quickly. So they were also waiting for some crystallization starting point, and then they formed very rapidly, but at the beginning not so. So, and here again, let's do a little bit of adding a little bit of water to see how this actually works. Yeah, all of the trapped air bubbles. Maybe, and by capillary action, it spreads all over the place. Then you will see that further you go away, then even though there's water there, the crystals do not seem to dissolve. And the reason is because the solution is saturated already. Once it's saturated, it cannot go it doesn't dissolve anymore. But further on the other side, where the liquid was still fresh, you see that the crystals here have already dissolved. And Yeah, and here on the other side, the solution spread, became more saturated, and the crystals are still intact here. So the thing is the following. There was a question. It looks like that. The urea. I thought it would be some kind of a liquid or powder. Well, urea is of course also waste products of mammals. So we produce this as well. It's a nitrogen waste product. And in this case, but it can also be artificially made. As a matter of fact, urea was the first organic substance, artificially made organic substance. Chemist, the German chemist Friedrich Wöhrer, he was the first person to artificially synthesize urea back in the 19th century. And yeah, at that time it was thought that only living things can synthesize organic substances, but he was able to actually create urea, make urea artificially. Yeah, so it is possible to make organic substances also artificially. Yeah, Friedrich Wöhrer was the guy. Yeah? And as you can see, it dissolves readily in water. And that's why we mammals, humans, use urea as our nitrogen waste product, and then it's filtered away and cleaned away by the kidneys. Yeah? So yeah, let's go on a little bit. I'm trying to speed up a bit. Aspirin, salicylic acid, number 8. This was difficult because it did not dissolve well in water. It dissolved only well in alcohol. And I just want to show you something. Here again, the desk view here. Look, I added a little bit of alcohol and immediately the alcohol started to spread all over the slide. And that's because alcohol has a very low surface tension. Yeah? So I did not even have to spread it across the slide. It went into that, yeah, it spread on its own. And yeah, so this is basically a salicylic acid, which is the active substance of aspirin, which is also known to make very nice and look and fine crystals. As a matter of fact, maybe we can try this a little bit, is to see how well it dissolves in water in comparison to alcohol. Okay, so again, a little amount of water I'm going to add. Okay, here we go. Okay, so that is with added water, and yeah, you see, they seem to remain largely intact, even though they are so fine, because it evidently does not dissolve very well in water. So, and as a little comparison, on the other side here, I would like to add a little bit of alcohol, and then let's see how it dissolves in alcohol. Okay, so I need to do the following, yeah. So that's my just regular alcohol. And here we go, just a second, 3, 2, 1. Up, and I think that made it very clear. Yeah, yeah, look how quickly it dissolves. Yeah, it also spreads very, yeah, the crystals disappear one by one. And the alcohol also evaporates, you see? Yeah. Then maybe we're able, because alcohol evaporates so quickly, maybe we're able to see the reforming of the crystals as well. Yep, here, do you see? Some of them are growing back again. Yeah. So that's actually an advantage of using when you've got substances that dissolve in alcohol, because the alcohol evaporates so quickly. Therefore, yeah, you're able to see the crystallization process much faster. Ha! That's nice. Look at this. Pew! It's not time lapse. It's in real speed. Looks cool. Yeah. Yeah, it looks pretty nice. Huh? And let's have a look again over here. This is the place where I had the water. And yeah, I think somewhere over here. Yeah. But yeah, no big difference. And here again. Yeah. So this is actually quite nice. Why not try this again just for the fun of it? So add a little bit, a tiny amount of alcohol again. The alcohol will spread very quickly because of the low surface tension. Get it a little bit into focus. See how it dissolves. It spreads incredibly fast. See a little bit if we're able to make it a little bit, increase the contrast a little bit. Yeah, and I think did it already start to recrystallize that quickly? I don't know. Ah, here we go. Look. Yeah, there where there are those alcohol droplets is where it started to recrystallize. What about here? Nope. Yeah, there was a little droplet here, and there where it was, where the alcohol was, basically that's where it started to recrystallize. Okay, let's move on. Let's move on a little bit. So this was salicylic acid, potassium ferricyanide. It's also a nice one. Looks nice and red. Okay, nice and red over here. This one is, I think we can even use, crystals here. Yeah, look yellowish. That's basically not in polarized light now. And here too, I think this dissolves better in water. Let's add a little bit of water and see how this works. Again, blip. Yeah. And however, again, this might take a significantly longer time to recrystallize because the water takes more time to evaporate. Okay, so just what I'm going to do is the following. I'm going to just like for the look, there's a little bit of recrystallization happening here. Just like for my other slides that I have, I've bought some antique slides. Last week I showed them all to you. And then I'm now making individual videos. I'm going to also make individual videos for those crystals here. Yeah? So where maybe I'm going to pick the nicer ones a little bit, and then I'm able to make separate short videos concerning those crystals. Yeah? And next thing is sulfur. Okay, so I gotta be honest with you, the sulfur was a really difficult one. I thought that it actually didn't work at all. Okay, sulfur looks like this, but I did see, so it's clumps like this, looks, like, I don't know, like anything, like almost like kind of soft rock, okay, and what I've got here is I tried to dissolve it, and it didn't really like to be dissolved very easily, but I was able to find at high magnification in some places, indeed, some crystals here, those tiny things that you see over here. And I think I just need to optimize this a little bit, but you can see it looks like those tiny branched structures that you see here. A dust fiber. Yeah, but over here, for example, these are the chunks of crystals, but only on certain places I was able to see those fine. Not anymore. It takes a little bit of patience to find it. I was able to see those fine branched structures of crystals. So this is one that is here again. So this one is one that I have to try to optimize a little bit. Okay, a Lichtenberg figure, like exactly like you do this with electricity, right? Where you have this where you put. It's kind of dangerous a little bit. Sometimes if you don't know what you're doing, but essentially it's like sparks forming from in high voltage. So the question was, is exactly, does it not smell bad at all? No, not at all. It almost smells neutral, because the sulfury smell, which smells bad, that's the so-called the rotten egg smell, is actually hydrogen sulfide, H2S. But this seems to be pure sulfur. Okay, so it's not it's not in the form where it's actually smelling bad. Okay, so this is just it's not hydrogen sulfide. Oh, what are these blue dots there? Interesting. Okay, so what I'd like to do now is I would like to show you a little, because that was now all of the 10 samples. Okay, but I would like to show you now also a little different one that I would like to demonstrate to you. Is a very unique way of actually making crystals, and that is by using a match. Okay, just a second. I need to get my plate again, because otherwise that's, yes, so here we go. And I need to twist the camera a little bit, because I do not want the fire to actually go into the camera. Okay, and I would like to show you something now, because I'm going to show you crystallization by sublimation, as it's called. Let's wipe the water here. There's still some of the pepper on the paper, on the plate. And what we now do is I put a match on alcohol. I want to put the alcohol away as well, for obvious reasons. Okay, you put a match here on the slide, and I'm going to light the match now from the top, and this will cause vapors from forming, and those vapors will crystallize on the cold microscope slide, and we can also observe this under the microscope. Okay, so, and okay, that's it. Okay, so we see that there is some kind of a deposit here. Okay, and let's put this under the microscope. Okay, so this is still the old slide. This one with the sulfur. And here, this is now the match. And we need to now be again a little bit patient and find the right place. Usually it's somewhere on the sides a little bit. Usually somewhere on the sides where the heat was not quite as high. And yeah, we can already see some interesting structures here. Okay, but that's actually not the one that I wanted to see. There were these typical, let's go on the side here a little bit, maybe here, maybe here. Here we go. Yeah, it's not directly in the center where the fire was, but further on the side where it was a little bit colder. Let's go up. We are able to see crystals. Okay, these are the crystals that were deposited. Yeah, and yeah, of different shapes and sizes again. And this is crystallization by a process called sublimation, where the gas goes directly into a solid state. Yeah. So you just take a cold microscope, and now actually I can go up with the magnification yet further, because it's so thin that, let's move this here up here as well, a different filter, so that we can change the color again. Ah yeah, this is better. So, and if I want to now preserve this, then that's quite easily done, like I have done before. Look, square ones. Then I'm going to just do the following, as I've done before. I'm going to simply place a cover glass over it. So, and here we go again. Now I can actually, yeah. And I'm going to now take a cover glass again. I'm going to then also take again some of this nail gel again. This time I'm just going to do it like this and like this. This goes on top. Carefully press down a little bit. Because it's a gel, it's very viscous and it will not touch the central part. And then, of course, I need my flashlight, the ultraviolet flashlight. Yeah, I treat it for approximately 30 seconds or a minute, depending a little bit on the intensity. And then I have basically my or semi-permanent slide of those crystals. Okay. Because those crystals, obviously, if you touch them, they will come off. Yeah. I'm just going to leave it at this. Yeah. Maybe this is already enough. Yeah, the cover glass cannot be moved anymore. Okay. Of course, I'm able to peel it off with force, but yeah, you can always do that. I mean, so here we go again with the, yeah, again, a little bit too intense. And then we have to find it again, usually somewhere on the side. We're able to find the crystals again, hopefully. Yeah, if I find them. I don't know where they are. So here, yeah, here they start. Here they start again. Okay. And we go up with the magnification. Yeah, I don't know, it could be also sulfur or phosphorus or a combination of different substances. Yeah. So sublimation will give instant fully grown crystals, or will they still grow as it cools? Well, the cooling is so fast, so basically I think yes and yes. I mean, the crystals have to grow, obviously, but the cooling is and crystal formation is so fast that you can almost say it's instantaneous. So they're not going to grow now anymore because there is no substance around them that could crystallize. So the substance for crystallization was only present for a very brief moment as the match head was actually burning. Right, this is when the substance was present and in sufficiently high concentration, and then it went from gas directly into solid. Yeah? And now crystallization cannot continue because there is no more substance around to crystallize. Yeah, and so this is a fairly instantaneous event, yeah? But it is still a gradual process during the crystallization, yeah? Because the crystals were smaller at the beginning and then they had to form, but this was very, very quick. Yeah? Yeah. So gotta have that box filled. Okay. Somebody is, I think, referring to this box over here. Okay, that's might be something that I'm going to show you also very quickly. Okay, because it's already slowly time to finish. Look what I've got here. Yeah, I found some hinges now for this. For those of you who don't know, I made this with my laser cutter. I made myself a slide box. The reason why I put the logo on here so that I do not accidentally open it with the wrong way around, right? That's why a logo or some kind of sign is really important so that you know which side is up. And here I found some small hinges. And the problem is I did not find yet a thing to close it, so maybe I'm going to think about magnets or so, but essentially this is how it looks like. Okay, so this I designed this with a laser and with a laser cutter. I made those. Yeah, it looks fine. Yeah? Yeah. So this is kind of the thing. And last but not least, I'm going to quickly. So there is an interesting. Hey Oliver, I found Chinese no-name. Chinese no-name of some planned objectives that look identical to the AMScope. Is it a generic brand and should I purchase? I'll be honest with you. Many of those microscopes, like from AMScope, Swift, whatever, all of those microscopes in that range use objectives that basically are made somewhere in China. And if you go to AliExpress, for example, you're going to most likely find very similar, if not the same objectives. So chances are pretty good that if they look the same, that they are also the same. Okay, because there are not so many manufacturers of objectives around that actually make those. So I would say that chances are pretty good that they're the same ones. Okay. Okay. To crystallize sulfur, you need toluene. Ooh, isn't this a little bit dangerous when you inhale it? But still, I don't know. Maybe acetone will work as well. I don't know. Okay. So this is something that I have to still try to figure out. Yeah. So let's check if I did not forget any of the questions here. Yeah. I hope there are no questions. There's one question. Are you saying that I could crystallize my own urine? Check my YouTube channel. I actually did that once as well. Yes, you can do that. The crystals actually look quite nice. You put a small drop of your urine on a microscope slide, you spread it, and you allow it to dry. Yes, the crystals look very nice. Okay? That's it is possible. Yes, urine does contain a lot of salts and many different minerals which will crystallize out. Yeah? And of course also urea, obviously, right? Which we just had a look at. Yeah, so yes, this does work, and as a matter of fact, I have also done that before. Yeah, So try soy sauce as well. I made a video as well. Soy sauce also works quite nicely, and table salt also works nicely. I think the crystals are not that, just by pure table salt, are not that interesting. Because they're just square, but if you experiment around, you're also able to do that. Sugar will also crystallize, but it will take a very long time. So you have to make a very syrupy sugar solution by heating up the water sugar mixture in a microwave, and then you have to allow it to evaporate. It usually takes a couple of days, and then you also will get crystals, right? So this is something that I'm going to leave it at that today. Again, this is not going to be the last time that I'm going to be using those chemicals. Again, a big thank you for having sent me those chemicals, those substances. Otherwise I would have not gone out and to buy those. I have to be honest, right? Because usually they are sold in much larger quantities, which I would not have needed. But in the smaller quantities like these here, they're really great. And they can also be used for other interesting experiments as well. Okay, and I think I'm just going to leave it at that for today again. Okay, so I'm just checking if there are some remaining questions. Would you seal a slide with blood with a nail gel too? I see no reason why not. You see, try it out. There is only one thing that I just wants to make you aware, and I'm going to do that now just as a last thing. The nail gel is not quite as strong as probably a nail polish. So it is possible, I think it is possible to, if you use a little bit of force, maybe it's gonna break or not break, I don't know. It is possible to lift it off again. I broke the cover glass. Yeah, so as you can see, if you probably apply the nail gel on all four sides, it's gonna be pretty stable. Okay, but this one, if you try it, I better not hurt myself. Yeah, I would say it's stable enough. Yeah, for all practical purposes. Yeah. I probably would not make commercial slides using this technique, but for hobby purposes and for quickly protecting your slides, why not? Yeah. Okay. So you can actually see this way that something which was a gel before is now quite solid. Yeah. So, but again, yes, I have to be careful. Otherwise, I have another sample to put under the microscope, namely my own blood. Okay. So I'm going to leave it at that. Again, big thank you for having sent me those substances. Okay. Hope you liked it again. please do consider subscribing to the channel. It's also not only to my channel, but to everyone who's doing hobby microscopy online on YouTube. Support them a little bit by also subscribing to their channels so that people can see that it's a popular hobby. Okay, I wish you all the best. And see you around next time again. Happy microbe hunting. Bye bye. Bye bye. All the best. Have a nice week.